Having considered the philosopher's approach to dimensional analysis, let's now consider the mathematician's approach. The mathematician's approach is to say that the Navier-Stokes equation, which is the momentum equation for a viscous fluid, combined with the conservation of mass, gives us a set of partial differential equations that must be satisfied in our space. Given a set of boundary conditions and the physical properties of the fluid, the equation has a unique solution. Now actually the poor mathematicians have yet to prove this formally, but we'll leave that problem to them. So let's say that we've defined our inlet velocity, which I will call v1, our density, ρ1, our viscosity, μ1, and the size of the box, d1, then we can calculate, using our CFD package, our unique solution to the Navier-Stokes equation. And let's say I have another little box here that is exactly the same shape but a different size, so it's geometrically similar, and the boundary condition there is speed v2, density ρ2, viscosity μ2, and size d2, then a good mathematical question is, when is this unique solution to the Navier-Stokes equation for this box the same as the unique solution to the Navier-Stokes equation for this box? In other words, when do these two geometrically similar but different sized boxes have the same solution inside them? Well, what we do now is define reference length scales and velocities and mass scales for both boxes so that we can write the governing equations in non-dimensional form. So, for the big box, we take the equation and we replace the variables in this column with the variables in this column. And for the small box, we do the same thing. In the equation, we replace the variables in this column with those in this column. And note that the del operator has units of 1 upon length. Therefore, when we see the del operator, we replace it with the non-dimensional del operator divided by the appropriate length scale. So now we turn to our Navier-Stokes equations written in dimensional form, and for the big square in dimensional form it's this equation, and for the little square in dimensional form it's this equation. And we substitute in the expressions on the previous page, and everything cancels wonderfully until we get to these non-dimensional forms here. And these equations are identical, except that for the big square we have a number μ1 over ρ1 v1 d1, whereas for the little square we have a number μ2 over ρ2 v2 d2, and that number is a non-dimensional parameter. It's 1 upon the Reynolds number of the first box, and it's 1 upon the Reynolds number of the second box. So here's the point of this. If these two numbers are the same, i.e. if the Reynolds number in the first box is equal to the Reynolds number in the second box, and of course if the boundary conditions are the same, then the solutions to both equations are the same. So using the mathematician's approach, we see that in this situation the only important parameter is the Reynolds number, which is what we'd also deduced from the philosopher's approach. So let's now return to a plot that we had in an earlier chapter. This is the drag coefficient CD as a function of Reynolds number for a sphere inside a flow at speed v, in which the sphere has diameter d and the fluid has density ρ, viscosity μ. But from the philosopher's and mathematician's approach, we know that the only important parameter made from all of these is the Reynolds number, which is equal to ρ v d upon mu. So if I plot CD as a function of the Reynolds number, then each point corresponds to a solution of the non-dimensional Navier-Stokes equation, and whatever the individual values of v, ρ, mu and d, as long as the Reynolds number is the same, then this is the solution to the drag coefficient. Now this is valid for all smooth spheres. If we introduce surface roughness, then we introduce another length scale, which is the bump height epsilon, and if we do that, then we introduce another dimensionless parameter, which is the bump height epsilon divided by d, the diameter of the sphere.